Welcome everyone. It's a great pleasure to have Professor Pedro Ferreira here today. Thanks a lot for accepting our invitation. Pedro is currently Professor and Head of Astrophysics at Oxford University and Director of the Beecroft Institute of Particle Astrophysics and Cosmology. He studied and worked at Imperial College in London, University of California at Berkeley, and at CERN in Geneva. He has held visiting positions at the University of Edinburgh and the Albert Einstein Institute in Berlin and Columbia University in New York. He won the Gerald Whitrow Prize in 2022 and the Eddington Medal 2024 of the Royal Astronomical Society. His area of expertise in cosmology, where he has studied the radiation left over from the Big Bang, the nature of dark matter and dark energy. He has led the way in studying alternatives to Einstein gravity, to Einstein theory of general relativity. He has also focused on the theory of analysis of gravitational waves and the use of machine learning methods in the analysis of cosmological data. His book, The Perfect Theory, A Century of Geniuses and the Battle Over General Relativity, was shortlisted in 2014 Royal Society Winton Size Book Prize. Today, he will present the battle against the undetermination of dark energy. Pedro, please, you can start when you're ready.
Well, thank you, Eleonora, for that incredibly detailed and thorough and flattering introduction. Thank you so much for inviting me to talk at this Zoom seminar, which has become such an institution. I see you have great speakers here, and so I'm honored to be on it. I've also rapidly scanned through the participants, and I see a lot of friends, and thank you for attending. This is something that I've been working on for a number of years. And now how do I go forward? Don't like that. Right, here we go. And it's based on work done with a graduate student of mine, William Wolf, who graduated about a few weeks ago. Carlos Garcia, who's been a postdoc at Oxford for the last 5 years. Declan Bartlett, who was a graduate student of mine, was in Paris and now is back with a fellowship, with quite a prestigious fellowship at Oxford, and Theo Anton, who was a graduate student at Queen Mary. And it's led to a bunch of papers, which you can look up if you are interested. And the setting is this: we're cosmologists, and we are very smug about what we do. We're full of ourselves because we can show plots like this. As you know, this is a plot of the angular power spectrum of the cosmic microwave background. The red is the theory. It is basically the theory that Bond and Evstathiou predicted in 1987, that if you looked at the anisotropies in the cosmic microwave background, you should pick up a curve that looks like this, with these bumps and troughs with a damping tail and with a flat part on the left-hand side. The data is the data from the Planck satellite, the 2018 data release, and it is a remarkable agreement. We have this exquisite theory with a handful of parameters that fits the data. And because the theory fits the data so well, we can use it to estimate the values of the parameters. And we do that, and we generate tables that look like this. This is from the Planck 2015 paper. And what you find is that you can constrain certain parameters with exquisite precision. And just as an example, this is from the 2015 data. With the 2018 data, I think, and the DESI data, you can do even better. You detect the presence of something, let's call it the cosmological constant, at 52 sigma. So this is really a remarkable situation to be in. We have a beautiful mathematical model of the universe. It fits the data beautifully, and we can fit the parameters of the model with exquisite precision. More recently, things have changed, and they've changed dramatically over the last couple of years, most notably because of the work of our colleagues working in supernova cosmology, but also because of our colleagues looking at the large-scale structure of the universe and trying to pin down the expansion rates at late times using things like the baryon acoustic oscillation. And this is a wonderful plot that the DESI team did, basically mapping out how we measure what we measure, and I think it's more of use for public talks, but I think it's quite remarkable, where you map the age of the universe against what is effectively the scale factor, and you can see where the measurements lie, and you very clearly detect that the universe is not an Einstein de Sitter universe. It's a universe that must contain something, some form of dark energy. It might be a cosmological constant or something else. Further, they say that it's not a cosmological constant, and that it is some time evolving cosmological constant. And the rules of the game at the moment is that we can describe what this extra stuff is as a fluid, which has an equation of state. And to keep it simple, we parameterize this equation of state as some model, which I write down here. The equation of state has a constant term and a term which is proportional to the scale factor. And what you find is you go away and constrain these with the current data. And while you might expect this to lie on W naught equals -1 and WA equals 0, it doesn't. It lies away from that point. What is that point? That point is a point where the dark energy is the cosmological constant, and it would seem that we're detecting some time-evolving dark energy, which is not the cosmological constant. And that is the state of play at the moment, that it would seem that current data is measuring something more interesting than just a cosmological constant. Now, why is this interesting? This is interesting. We have to take a step back and think of what is this world that we live in. We're not only content, we're of course we're content that we have a physical model for we have a model for cosmology, which is based on physical principles, on statistical mechanics, on general relativity, on elements of plasma physics. But for the last 50 years, we've wanted more from cosmology. We've wanted to use cosmology to learn something about fundamental physics. And this is just a snapshot of some of the books that I have on my bookshelf that I was brought up with. These are books which claim that if you use cosmology properly, you will be able to figure out what the universe is made of. Not in a rough way, but in quite a precise way. Specifically, the idea of this cosmology that we now believe we're doing with fundamental cosmology, or what I often call particle cosmology, is that we know what the action of the current of the universe is. In terms of the standard model, we know what baryons do, and it's described in terms of the Einstein-Hilbert action, the standard model, etc. What we're trying to do with cosmology is we're trying to figure out what the rest of the universe is doing, what we sometimes call the dark sector. For example, for this dark energy that seems to be popping up with the DESI data and the supernova data, we're trying to figure out what is the fundamental action of this dark energy. If it's a scalar field, what is the action for this scalar field? Now, this is an incredibly ambitious goal, and it is problematic because there are many, many proposals. There are many, many proposals for what dark energy might be. And over the last 30 years, we've accumulated a huge number of propositions. There are big review articles proposing what dark energy might be. But the problem is that a lot of these proposals will predict basically the same thing from the point of view of what we can observe. And one way of thinking about it is that if we look at this W0 WA plane and we consider a bunch of these proposals, they'll all more or less predict the same values of W0 and WA. So we're faced with this worry, this problem, which is what I call the underdetermination problem, which is, can cosmology actually figure out what the fundamental action of the universe is? More specifically, for the purpose of this talk, can cosmology actually figure out what the fundamental action for dark energy is? And that is the problem that concerns me and that I'm trying to tackle with, and that I will talk about today. Now, this reminds me of a paper that was written in 1954 in the British Journal for the Philosophy of Science. And it was a debate between a mathematical physicist, Gerald Withrow, who was also interested in astrophysics, and Hermann Bondi, who you all know. Hermann Bondi had written a book on cosmology. It was basically a book presenting the case for physical cosmology. That we were entering a stage in 1954 where the rules of science could be applied to cosmology. We were collating data, we were making measurements, we had a theory, and we would be able to tension the theory against the data. Now, Withrow said, well, that's all well and good, but look at cosmology now, i.e. in 1954. Cosmology now isn't very different from cosmology 2 millennia ago. It's very much based on opinion. People have their own opinions on what works and what doesn't work, or what is a sound physical principle, and they stick to it. And he used the example of the debate that was going on then, which was the universe described by a Big Bang or by the steady state? And let's just look at this in a little bit of detail, or briefly to some extent. The Big Bang model assumed 3D homogeneity and isotropy of the metric, and assumed general relativity. And if you, as Friedman did and Lemaitre did, if you turn the handle, you could work out how the universe would expand, what it would look like in the past, and it would evolve. And one of the interesting consequences, which was pointed out as a pathology by people like Bondi and Hoyle and others, was that there was an initial singularity, a Big Bang. There was a point at the beginning where physics would break down. And this was difficult to stomach, according to these people. Big Bang was actually a pejorative term, which was coined by these people. The counter view was the steady state model, where space-time itself was homogeneous and isotropic, and you could use the laws of general relativity. But for that to work, you had to posit the existence of something, what they called the C field, something which would lead to the continuous creation of matter. Now, the amount of matter that was created was microscopic. By any other means, it would be undetectable, but it was an assumption that you might have. But the debate from the point of view of data is either one of these could work, and the physical principles that one would assume and the beliefs that you had behind each one of these were basically equivalent. You could either pick one or the other. Whether you picked Big Bang or the steady state was an aesthetic choice. It was based on opinion, okay? Now we know how all that happened. That got resolved. Martin Rees mapped out the evolution of radio galaxies, the cosmic microwave background was discovered, etc., etc., etc. And we know that the steady state model doesn't work. We firmly landed in the camp of the Big Bang. I think Bondi was proven right because of the plot that I showed you at the beginning of the talk. We have a accurate mathematical model which makes predictions and from which we can work out a plethora of things which are then borne up by comparison to data. But you may ask yourselves, if we're in a situation now in which we can ask the same kind of question, is particle cosmology a science? In other words, specifically, can we go beyond opinion in figuring out the nature of dark energy? Will we be able to home in and find what is the fundamental theory of dark energy with cosmological data? And I'll talk about some steps that I've taken towards this. I don't think we will be able to solve this problem, but I'll tell you what this way of thinking has led me to. Now, why are we in the situation that we are? We're in the situation that we are because of our colleagues who work on baryon acoustic oscillations and our colleagues who work on supernova. And I'm not going to go into the details of what they actually measure, but basically, with the case of baryon acoustic oscillations, they either make local measurements of the Hubble rate or the angular diameter distance as a function of redshift, while supernova, you measure magnitude, which is a measure of luminosity distances. And these are the latest DESI DR2 paper has these very useful plots where they plot a compound of what DESI measures, which is this DV, divided out by the fiducial model, which is lambda CDM. And you have this black line, which is where those data points should lie if the universe is described by lambda CDM. And on the right is the supernova data, and it's again, the black line is where those measurements should lie if the data was described by lambda CDM. And it's away from that, and it's arguably away from that at a high or low statistical significance. But let's just pursue that it is away from that. And so the question is, what does it point to? Now, I'm agnostic at the moment whether we are there. I've been around for long enough to know that anomalies have come and gone, and you might consider that this detection is an anomaly. I find the work of my supernova colleagues and my BAO colleagues very compelling and thorough, but I also know that sometimes things change. And you may want, people will say that you have to be aware of some of this data. You have to be aware of the supernova data. There might be an inconsistency between the different data sets. The low Z sample plays a very important role. But and all of this is true. People who work on this topic have counter arguments to this. But what I believe with regards to the supernova data is the data will get better. The data will get better, and some of these issues we will be able to resolve. So it's just a matter of time before we can completely believe the supernova data. So I will assume, well, I'll get to that in a minute. With regards to the DESI data, I think there's less to worry about. There are worrying inconsistencies with the Sloan survey. And George Efstathiou has pointed out a lot of interesting aspects on how you interpret the DESI data. But again, I'm going to wait. I'm going to wait because we are in the middle of what I would call stage 4 cosmology, where we're going to be flooded by more data. So in a few years' time, the situation will become clearer. So that's the first statement I want to make about the data. The second statement I want to make about the data is, how do we look at this data? Well, we don't really look at plots of angular diameter distances or magnitudes or Hubble rates. We typically look at what I call W-ology. And what does that mean? That means that in practice, we compress the data. We do something very simple. We assume that the Hubble expansion, or the expansion rate of the universe, has this simple form. There are little tweaks to it, but basically it has this simple form. It depends on the scale factor. There's a non-relativistic part, and there is a bit, let's call it the dark energy bit. And that this dark energy bit depends on a free function, W of A, in the following form. Okay? And so this free function, so the exercise is that you want to fit this model to the data. How do you do that? Well, as I said, we measure magnitudes, we measure angular diameter distances, we measure the Hubble rate, we measure this thing that I call dV, which is often used with baryon acoustic oscillations, and all of these things depend on H of A, okay? And so you have these measurements of mu, dV, dA, and H. We then given a model for H of A, we calculate these things and we fit these things to the measured values of mu, dA, dV, and H. Okay, so we fit the model, we fit the model to the data. In other words, we fit H of A of the data and we parameterize this H of A in terms of omega m, H naught, and this W of A. Okay. Now, one of the simple things you might do is say, well, WA is just a free function of A. It can be anything. But let's make a simple assumption. Let's just assume that it's some linear function of A. Then in practice, what we do is we estimate these quantities, W0 and WA. And that's all we're doing. We're basically taking a data set, we're taking a mathematical model, and we're compressing it down to a bunch of numbers like as I said, omega m, H0, and this W0 and WA. There are other numbers that come in, but they're not important. Okay? Now, you may be tempted to assign a physical meaning to W0, WA, and indeed, this WA is, as you might expect, the equation of state, if you assume that that dark energy has the form of a fluid. And we know that WA equals -1 is the cosmological constant, and that WA less than -1 is unphysical in some sense. It's what we call phantom. But you shouldn't do that, because this W0 and WA are estimated from the data. We have a mathematical assumption for the model, which is this, and we measure mu, dA, and dV, and we fit it, and we extract this W0, WA. So these W0, WA is just a form of data compression of the cosmological data. It's a useful form of data compression. And the key thing about this is that W0, WA will depend on the survey characteristics. And let me give you an example. Imagine that the universe was described in terms of fluid with a WA given by that black line, okay? And we went away and we took CMB data alone, or supernova data alone, or BAO data alone, or a combination of all of these three, and we tried to estimate what W0, WA would look like. You would get completely different values, or well, you would get different values of W0, WA, depending on your data combination. And the way to see this is a W0, WA, as I said, it's a linear function in the WA plane, and you get different lines. So assigning meanings to W0, WA is a mistake. It is merely a form of data compression. Okay, that's the first thing. So what do we see? Well, if we do the simplest thing, which is assume that WA is 0, you find that you basically get W0 equals -1, which is interesting, which is the cosmological constant. So if we assume that there's no time evolution, we get back what we've always believed in the past, which is that W0 is equals -1 and it's a cosmological constant. Now, if we allow WA to be free, interestingly, it pulls it away from W naught equals -1, and you get a time varying WA. This WA, which if it was a cosmological constant, would lie centered on that point, isn't there. Okay? Now, there have been interesting points made about this. First of all, if you plot the constraints on W naught, WA, and you plot the corresponding W of A that you get from these constraints, they all seem to cross W of -1 at around about the point where the data is best measured. And that's an interesting point, and I think I should bring it up here. Okay, that's the first statement. Now, that doesn't really change the fact that you detect a time evolving WA. You could do the exercise of, instead of parametrizing WA, instead of W naught plus WA 1 minus A, you could choose your pivot point to be at that point where it intersects -1. And if you do that, what you find indeed is that that pivot point is W of -1, but you still find a time evolving WA. So you can't get away from the fact that the data seems to be indicating a time-evolving equation of state. Not only that, you might find that there's a coincidence that it crosses -1 where the data is best measured, but it also crosses -1 where the dark energy starts to dominate. So this is another coincidence. And you might worry about these coincidences, but my point of view is I'm not going to worry about these coincidences because they may be coincidences or not. It's just a matter of opinion. And I'm trying to shy away as much as possible from opinion in looking at dark energy. Now, another thing you might say that people say is, does it depend on the parametrization? We chose a very specific parametrization, which is here at the bottom of the slide, which is known as the Chevalier-Pulaski-Linder approximation, the CPL. But there are any number of approximations, and this is just an example of 4 different approximations. And you can go away and do the analysis and look at the data with these different approximations or parametrizations. And what you find is they may give you different contours because WA means something different for each one of these parametrizations, but they're all away from 0. So choosing a parameterization does not, different parameterizations does not lead you to different conclusions. Let's not worry about the choice of parameterization. I would say further, I believe that the data at most can tell you about 2 numbers, and let's stick to W naught WA, okay? I mean, people have attempted to try and parameterize W of Z in terms of more complex things like Gaussian processes or pivot point or spline points, whatever. I'm not going to worry about that for now. Okay. So from now on, I will assume that the data is correct and is fit for cosmological analysis. Let me be clear. I'm assuming this for this talk and for what I've been working on. I'm agnostic. I'm agnostic at the moment because I've seen enough of these shifts in data to know that this could go away. So at the moment, I am just exploring, if the data is correct, what might we say and how might we address the problem of underdetermination in cosmology? Now, this is an important plot because this is the starting point for everything I'm going to say here. And the starting point is the following. Imagine that you have a theory that predicts couple of observables or a couple of things like A and B. And one theory predicts this dashed ellipse over here. And another theory predicts a dotted ellipse, or I could have put any other volume over here. And then I go away and I measure what those quantities are. And they lie on top of this theory. I think it's unarguable that this theory is much better than that theory. I would say more. I would say that this theory is not a good theory and that there is not much reason to continue pursuing such a theory. One way of thinking about this is to think that the priors are sufficiently distinct from the likelihood for it to be a valid, for you to do valid Bayesian analysis. But this is just the simplest cartoon that I want to show of why, of my attitude towards how we look at theories. Okay? And so how do we compare with theory, given observations? Well, if you've got some fundamental theory, it'll depend on some fields, on some parameters. It'll depend on some initial conditions. It'll predict the observables, H of A, DAA, DV, all these things that I spoke about. And then you'll have a ton of data. all right? And you'll have a ton of data, and this data will have restrictions, will have limitations. It'll have a limited redshift range, it'll have uncertainties, it'll have covariances. And given this theory and the parameters of this data, it should be possible to predict, it should be possible to work out what would be the W naught and WA that you would calculate for each one of these theories, okay? And the result would be, given a set of a set of survey parameters, you can work out what are the priors that a given theory places on W naught WA. So this is the exercise that I'm going to use. Again, I do not think W naught WA has any fundamental meaning. It is simply a way of compressing the data. We might even call them observables if you want. And again, and I repeat that because W naught WA depends on the survey parameters. Imagine now, and I go back, I've shown this plot before, I'm going to show it again. Imagine now that I have some scalar field theory and it predicts this W of A. And I now figure out what, for this specific set of parameters for that theory, what are the corresponding W naught and WA. Depending on your survey parameters, you would get different W naughts and WA. So when you compare a theory to the data via W naught WA, you need to go through this process. You need to figure out what is the corresponding W naught WA associated to a theory. So I've established the rules, the general rules of the game. I will now focus on, I'm going to focus solely on scalar field models for dark energy. And there's a reason for it. For the last 30 years, these have been the bread and butter models that people have used to describe dark energy. Many non-scalar field theories effectively reduce to scalar field models when you look at the dynamics. So it's pretty broad. It's not exhaustive, but it's a pretty broad class of models that I want to look at. And the filter that I am going to use is going to be the filter of effective field theory. I am not interested in building models. I am interested only in saying, if I have a scalar field, what is the most general action I can build? If I use effective field theory, I know that the most general action I can build is the one that I have up here, which has some free functions of time. I could add the next order terms, making it more complicated. And the line below, I've just written three next leading order terms that I would have to add in. And notice that you have these free functions of the scalar field, which might be a source of worry. But it turns out that, okay, that's the first thing. So I would love to just tackle this completely generally, and it might be a completely daunting task. So what I'm going to do first is I'm just going to look at the simplest and most popular model for dark energy, which is thawing quintessence, or just a minimally coupled scalar field. If I have a minimally coupled scalar field, well, this free function just reduces down to 1, and this free function just reduces down to 1, okay? And the only degree of freedom you have is a potential. You need to describe a potential. Now, you may think, because of that list of potentials that I put up initially, that we now have to consider a huge number of potentials. But it turns out that you don't, because in practice, the most general thawing model you can describe in terms of the most general potential for a minimally coupled thawing is simply a quadratic field. You can get rid of the linear term and it's just a quadratic field, which will have very different behaviors depending on whether m squared is positive or negative. But this completely describes the dynamics of any thawing quintessence model. And why is this? Well, let me take an example. Let me take the axion potential. If you look at the axion potential, it has a 1 plus cosine term. But if you Taylor expand that potential, you will get something which looks like you'll get a constant plus a quadratic term. And why is that enough? That is enough because from the point of view of dark energy, we only probe a very narrow field excursion in its behavior. In other words, the data will only probe a very narrow range of field evolution for the scalar field. And this is just, I've just plotted this here, where you have the blue is the axion potential, the orange is the hilltop, quadratic potential, and the dashed line is how much of the scalar field the data actually probes. And it's an almost perfect approximation. And you can do that for any potentials. I would challenge you to come with a potential in which that is not the case, given the cosmological data. Okay? And so, given that that is the case, it is enough to look at quadratic potentials. You do not need to do anything else. Well, given that, it's really easy. We know what the most general thawing quintessence model is. It's just a quadratic potential. And you can work out its priors. And you go through that exercise, and this is what you find. You find that the most general thawing quintessence model lies on this wedge on the W0 WA plane. And it's just this, it's triangle. And thawing quintessence cannot predict, with the current DESI plus supernova data, a W0 WA outside that wedge. And where does the data lie? It lies over here. So we see that the thawing quintessence really is not a great model for the data. It's really not a great model for what we're seeing with current cosmological data. And you can now dig a little bit deeper, and you can decide that, okay, I really shouldn't do this because the priors don't overlap with the likelihood, but let's just do this. We get rid of the W0 WA, predict directly the observables, and constrain the parameters. And what do you find? You find that hilltop models are favored. In other words, it predicts a potential, an upside down potential. It's strongly favored. But if you then go away and you work out, for example, the chi-squared, it improves the chi-squared. That's not surprising. It's pushing the theory in the right direction. But the Bayesian evidence is really moderate, marginal. It's not very compelling. And so it's mildly better than lambda CDM, but inconclusive. But no, I calculated these Bayesian evidences, all of these, knowing that the priors did not lie on top of the data. So I would argue that there's really scant evidence for thawing quintessence. Okay, we need to do something else. Well, let's continue on this campaign of keeping the most general action for the scalar field. This, again, people might say, well, does it depend on the parameterization? It doesn't depend on the parameterization, and I'm not going to spend time on this. So what can you do, right? So thawing quintessence is really not a good explanation to the data if we believe the data. Well, let's go back to our effective field theory. But the next thing you can do is you can go and change f of phi, which is the non-minimal, how the scalar field is non-minimally coupled to gravity, okay? And if you do that, well, again, because of the narrow range of evolution of the scalar field, you only have a quadratic, you can parameterize it in terms of quadratic potential. Of course, if you parameterize one of the things in terms of a pure quadratic potential, you need to include a linear term in the other. So you will note that there's no linear term here and there's a linear term here. You're allowed one shift to get rid of a linear term. And I got rid of it here, but I have to leave it here, okay? So why is this interesting? Well, if you play around with it, you find that actually you will lead to the kind of behavior that we're looking for. So these curves on the left are a few examples of this non-minimal model where you see that it actually dips below -1 and then goes up. And if you then go away and your choice of data set, in this case BAO plus supernova plus CMB, and work out what the corresponding W0 WAs are, they lie bang in the contours. Now, you need to do this for the most general choice of parameters. So you need to sweep the whole choices of initial conditions, coupling constants, etc. And you do that, and you get this blue contour. So let me remind you, what I have here is the prior for thawing quintessence over here. So minimally coupled quintessence is over here, disjunct with the data. Non-minimally coupled lies bang on top of the data. So this is a much better model for what's going on in the universe. And if you compare it to if you go away and then do what you can do in this case, because the prior overlaps with the data, with the likelihood, you can work out the chi-squared, and it's a dramatic improvement in chi-squared. But more importantly, it's a dramatic improvement in the Bayesian evidence. It's very, very strong evidence for the non-minimal scalar field. I would argue there's overwhelming evidence from cosmological data that it's non-minimally coupled. Furthermore, the evidence for the non-minimally coupled theory is even higher than if I were just looking at the CPL model. So it's a really compelling microphysical model for the dark energy. And this is just our own version of the plot that was done in DESI, just to see why it's good. And it goes exactly in the right place. Now, given this, you can do inference. And if you do inference, you can work out constraints on the cosmological parameter, on the parameters of the potential, for example, as well as the other cosmological parameters. And what do you find? Well, you find that the non-minimal coupling constant, it's constrained to be of order 1, and you find that it's a Hilltop potential. And immediately you start to worry. You start to worry because it's non-minimally coupled, and we know that you know that non-minimally coupled theories are a problem, because non-minimally coupled theories predict fifth forces. And so you can work out what the fifth forces, what the amplitude of fifth forces will be for such a theory. And what you find is that your fifth forces, such a theory predicts fifth forces of order 10 to the minus 2, 10 to the minus 1. But this is an exclusion plot produced by my ex-student Jamie Bamber, who's now at Illinois, and it's a beautiful compilation of current data. And what does it show? It shows that it's completely excluded by current constraints. In other words, the non-minimally coupled theory as it stands would not pass astrophysical and laboratory constraints on fifth forces. So this is a problem. Now, one way of seeing this is if you look at the effect on the Newton-Poisson equation, there is a correction to the Newton-Poisson equation, which is typically encapsulated in mu. You might think of it as the effective Newton's constant. And what you find is that if it was GR, it would be equal to 1, but it deviates from GR as you get close to Z equals 0. And it's deviations of order 1, so substantial deviations. Okay? So how do you solve this problem? Well, one way of solving this problem is to add one of the next order terms in your effective field theory. And one term that you can add is an x squared term. Remember that x is a kinetic term, right? And if you do that, it turns out that you get Weinstein screening. In other words, you get screening such that on scales close to a massive object, the fifth forces are suppressed. And you can actually work in detail, and it's very different from other Weinstein screenings that have been worked out before. You can work out what the Weinstein scale is. The problem, of course, is you've had to add in another term. It turns out that the sign of this term is the wrong in terms of other physical principles, and that you've got to pick a physical scale which is lambda, and this lambda is an energy scale of 10 to the minus 2, which corresponds to quite a substantial lambda. So not only do you had to pick a new energy scale, you have a wrong sign, and you've opened up a new world of problems. So it seems that you go down this route of non-minimal coupling and things just get more and more complicated. All right, so you say, okay, let's not do this. What other ways can we try and fit the DESI data? Well, let's go back to our effective field theory. Our effective field theory, as I said, we had the top bit, which is up here, and we have bottom bit down here. And what other, how could we try and find something that might fit the data? Well, you might want to get rid of the potential. You might want to get rid of the potential. And you want to add these extra terms, end up with models that have been well studied before. They're Galilean models. These are extensions of Galilean models. They're shift symmetric. They have this nice physical property that they satisfy a shift symmetry. They give you phantom equation of states, but the problem is the equations of states never cross -1. So you go away and do the exercise that I told you about, which is given a data set, the parameters of a data set, what are the corresponding W naughts way, and it lies in completely the wrong region. So from the point of view of the shift symmetric of effective field theories, just looking at shift symmetric models, it won't work. Well, it turns out that you might do something else, which is, okay, let's get rid of all these higher order terms and just keep the lowest order term, which is what is known as the cubic Galilean term, and just add a potential, just a quadratic potential. And if you do that, what might it work? Well, it does work. You go away and do exactly the same exercise, and you find that you actually can, again, produce the W naughts and WAs, which are predicted by, which are measured by DESI and the supernova data. So this is another route. It seems that this is another route, which is not the standard non-minimally coupled theory route, which has the problems that it has. It's another route, which has this physical principle behind it, shift symmetry. We've had to break it with a small mass, and we get a model that fits the data. And if it fits the data, we can go away and we can do inference and we can calculate the various parameters that go into this theory. We can calculate the chi-squared. The chi-squared is not as the difference in chi-squared is not as great for as the non-minimal model, but it's better than thawing quintessence. The Bayesian evidence is borderline strong. It's around 5, so it's still, you know, it's a possibility. Okay, but then you go and do what we did for the non-minimal theory, and we look at, for example, what does the effective Newton's constant look like? And while for the non-minimal theory that I'd looked at before, you had this blue line, for this theory, again, you have this red line. In other words, you get of order 1 deviations from general relativity. You will have fifth forces. And so again, you'll violate the constraints which are of fifth forces on astrophysical and laboratory scales. So how do you solve this? Well, the interesting thing about these theories is they already have a Weinstein screening mechanism in them. It's a cubic Galilean, which has been studied to death over the last 10 to 15 years. The problem is, of course, that the energy scale, you're not free to choose this energy scale. You might see it as an advantage. You might see that everything is built into it already. But the energy scale is of order 10 to the minus 13 electron volts, which corresponds, and this energy scale is the scale at which the theory breaks down, which unfortunately is a length scale of order 10 to the 3 kilometers. So the theory breaks down on macroscopical scales, not on cosmological scales, but on macroscopic scales. To give you an idea of what the Weinstein screening scale for the Milky Way is, it's about a few megaparsecs. But you face the problems with this theory that you had already faced with the cubic Galilean and other theories like massive gravity, which is your theory is not predictive below 10 to the 3 kilometers on. So in other words, you can't go away and do calculations, for example, in the laboratory. It doesn't work. Furthermore, the kinetic sign, as you can see over here, has the wrong sign for this to work. So again, you're entering a world of complications. You're trying to do something, but your theory just gets more and more complicated. If you wanted to try and solve the strong coupling regime, you have to come up with some way of fixing this. You'd have to add more terms, and your effective field theory breaks down. So, you know, where are we? We clearly need some form of non-minimal coupling. Okay, we need some way of non-minimally coupling the scalar field to the gravity sector or to the matter. But we also need to protect this non-minimal coupling from fifth forces. And one way that's been explored in the past is by adding higher order Galilean terms, quartic or cubic or quintic Galileans, adding in more complications. Another possibility is that you change this, it's non-minimally coupled, but you only see the manifestation of this non-minimal coupling between the scalar field, the dark energy, and the dark matter. And one way of thinking about it is this coupled dark matter, dark energy. And for those of you in the know, if you work, it's easier to think of this in the Einstein frame. I always talk about it in the Jordan frame, but it's easier of thinking about it in the Einstein frame. You switch off all the non-minimal couplings to baryons, okay? So these are the possibilities. But what I'm seeing is that we're entering what I've called the Ptolemaic era of dark energy. If we want a universally coupled theory of dark energy, which would be simple, then we have to add fixes at each stage, and a simple scalar tensor theory won't do. If we are adding epicycle upon epicycle in our attempts at constructing a viable model of scalar dark energy, we're back to opinions. What do we consider acceptable? What do we consider valid? What do we consider, you know, what is a nice theory? What is a theoretically motivated theory? Where are we going? Well, this is the future, and this is just a cartoon of where we're going. And this is really a cartoon. This is 2024, where we are now, or where we were a few months ago, or it's 2025 now, so those arrows have constrained. This is where we will be by the end of stage 4. There will be improvements, but there won't be dramatic improvements. I mean, I think it'll be great if we end up down there, and especially if those contours move a bit further down, because then we'll be in a really dramatically uncharted regime of dark energy. But this is where we're going. This is not going to shrink to a point. So the underdetermination problem is real. Is dark energy unknowable? Well, Lambda CDM is a remarkable fit, and there's no way we can get away from that. It's a remarkable fit, and it does incredibly well. We have this anomaly now. Is this anomaly enough to ditch Lambda CDM? I'm not at all sure. We can do better because we can describe scalar field, we can come up with models of dark energy which fit the data better, but they involve non-minimal coupling. They involve non-minimal coupling which lead to ancillary gravitational effects. It's straightforward to explore these theories quite exhaustively because we only probe a very narrow range of the scalar field evolution, so it's enough to consider polynomial couplings or Taylor expansions of whatever free function you're allowed to do from the point of effective field theory. And the data will improve constraints by a factor of only a few in the next 10 years. And we should bear that in mind. We're not going to see this huge step change in the data. DESI and supernova have already brought us that step change. Now, what might happen? That constraints will improve to a strange, unique region of model space, which means that those contours will migrate and go even further down. And that would be super interesting. They might not. They might migrate up and land on top of lambda CDM. And then, as we know, there are a ton of thawing quintessence models which would lie there as well as lambda CDM, and underdetermination would remain. It would be a matter of opinion whether you believed in lambda CDM or thawing quintessence. More interesting is that there might be new, as yet unknown, non-cosmological measurements that might detect dark energy. And one way of thinking about it is that in trying to build these, figure out what theories of dark energy are consistent with the data, there are all these ancillary gravitational effects. There might be measurements which are non-cosmological, which might detect some of these ancillary gravitational effects. But they must have a unique signature. Otherwise, again, different people might construct different versions and you wouldn't be able to tell them apart. And you're facing the problem that the mass scale of dark energy is so small. And mass scales of this small are really only probed on cosmological scales. Now, there's interesting speculations that one might have. One might speculate that scalar field dark energy may be incompatible with the data. If the contours really migrate to a region where you can't do it without having completely unacceptable consequences on other scales, that would be interesting because you would rule out a substantial landscape of model space, and that might actually lead you to revisit the paradigm for cosmic acceleration and rethink how we are modeling what is going on in the universe. And that, I think, would be probably the most interesting consequence. If we're just going to try and fit dark energy models and we find multiple fits, it's not interesting. It would be interesting if we were able to rule out the largest possible swathe of dark energy models and make us rethink what's going on. Now, the way that I think of cosmology, I think the analogy that I've come to use is the example of Einstein on Brownian motion. Einstein in 1907 figured out Brownian motion. He was able to come up with a mathematical model for why grains of pollen migrate and random walk across water. And in doing so, using the statistical mechanics of fluids, he was able to infer that there was an atomistic or molecular structure to water. And not only that, he was able to determine the typical size and the typical speeds of these molecules that were leading to this Brownian motion. He was able to infer properties of the water. What he was not able to do is he was not able to infer the molecular structure of water and the atomic structure. The Brownian motion, is simply too blunt a tool to figure out what atoms are made of. For that, you needed spectroscopy. I would argue that cosmology might be the same. Cosmology is a great blunt tool to figure out some bulk properties of what dark energy is, but we need something else. We need to find the equivalent of spectroscopy for dark energy. And this reminds me of a quote that I read in Wigner's, and the problem is I can't read this because I've got the Zoom stuff on top. If I exit like that, can you still see it? Okay. Wigner's memoirs, recollections, are really interesting. And in 1925, he was visiting Einstein. Einstein was in Berlin at the time. And there were all these people hovering around. And he said that until 1925, most great physicists, including Einstein and Max Planck, had doubted that man could truly grasp the deepest implications of quantum theory. They were in fact that man might be too stupid to properly describe quantum phenomena. Men at the weekly colloquium in Berlin wondered, is the human mind gifted enough to extend physics into microscopic domain, to atoms, molecules, nuclei, and electrons? Many of those great men doubted that it could. And it may sound that I'm saying something like this. And it's worrying that if I am, because we know what happened next. What happened next was this. which we are almost celebrating the 100th anniversary of. Heisenberg went away and he basically got hold of the data and completely reformulated how we understood atomic structure and came up with an explanation which people then very rapidly used to build up a theory of the atom. One would hope that that might happen with dark energy. And I'll end there.
Thank you so much. Thank you for the very nice talk. Do you have any questions? Andrew?
Hello. Thanks, Pedro, for an excellent talk. I have a few points I want to make if I can stretch your patience a little. I think it would be useful. You had a nice slide that just showed a good model and a bad model in a two-dimensional space. And that would be quite a nice, quite near, maybe, yeah, 10 slides. And that'd be quite a nice point of focus to talk around. Obviously here we're invited to think that A and B are W0 and WA.
For example.
And that there are two different theories, one that fits the data and one that's not. But the first comment I wanted to make is that this is not really the kind of comparison that we're making when we're talking about whether or not there is dark energy. And certainly, I mean, I agree with everything you've said. And for sure, if the dark energy really does turn out to be evolving, then I expect there will be many degenerate interpretations of what that means that we will never untangle. Equally, I'm not yet anywhere near ready to concede that the dark energy is actually evolving for reasons given in many places. But anyway, the theories we're comparing, you've drawn two different sets of two-dimensional contours, but of course the lambda CDM model, for example, is not a contour in the W0 WA space, it's a delta function located at some particular point. And I think this issue of the dimensionality of the models is an important thing, which makes the lambda CDM model more credible. Now that feeds into the issue of priors. So here, as it happens, you put the data not too far apart. So although you said that theory 2 is not interesting at all in this case, if it's really a kind of a 3 sigma distance, I'm not sure that you would necessarily say that. But I think that the trend we've seen in recent years in dark energy, and also I think in addressing the Hubble tension, is we've been forced into a regime where we routinely consider many models which we used to think were a priori extraordinarily unlikely. So you and I have been around a long time, and everyone's talked about lambda CDM for as long as we've been alive, and lots of people thought it was a good model. Against that, the favored current models against DESI plus the CMB plus supernovae have a whole pile of unlikely properties. They are phantom models. They have phantom crossing. The phantom crossing occurs in the center of the observational window. The W0 is small, but the WA is extremely large. And each one of these things separately we would have thought was very unlikely. So by the time you've multiplied together a few factors of a few or factors of 10, a model that might fit that data well, viewed 20 years ago, might have been thought 1,000th as likely or 1,000,000th as likely as the lambda CDM model. And this kind of is very hard for data to overcome prior dependencies of that strength.
So my worry with my worry with what you're saying there, with the other thing I agree with lambda CDM, but what you're saying there, no price on W0 and WA. There are prices. I mean, you have to decide what your forum, your scenario is, what your playground is, right? And I'm saying if you consider a scalar field model, well, you write down an action, and then you have initial conditions, you have parameters in your theory, and that's what sets your priors, right? And then you have to see if it is unlikely or not. The fact that WA is large and W0 is -1, all of that is, I think, opinion, right? Opinion goes all the way back to me setting priors on the parameters of the scalar field. I will give you that. But I think that's where I'm setting up my priors, and that's what we're discussing about.
Yes, I completely concur with what you're saying. It is opinion, and everyone's opinions can differ, and I think it's important to remember that many people's opinions are going to differ for these reasons.
Yeah.
The other, to come to an actual question, though, is you find if you embark on the thawing quintessence angle that you're forced along certain directions. So the non-minimal coupling appears, and then it has to be screened, and then you can look at shift symmetry. And you do find yourself in regions of the observational W0 WA plane that fit the data quite well. And my question was, it wasn't clear to me whether or not the models you're discussing are genuinely phantom crossing models with whatever problems that might entail in terms of dealing with perturbation equations and other things, or whether they are just looking like they're phantom crossing models in the W0 WA plane, but in fact are physically well defined in all regimes.
So it's complete. So the non-minimally coupled theory is completely well defined. Here it is. Where is it? This is completely well defined, and I think you're actually bringing up precisely one of the issues with WA, which is when we figure out WA or W0 WA, we are assuming this model, okay? But if you work out the equations of motion for any non-minimally coupled theory, it does not look like this. It's not Einstein's equation equals to stuff. There's all this other stuff going on. And so the issues with phantom to do with negative energy negative kinetic energies and all these issues that are, I think, are specific, are if you interpret it as a fluid with an equation of state with certain properties. But extensions of Jordan-Brans-Dickey don't have that.
Okay, great, thanks.
Thank you. Indranil?
Yeah, so I wanted to ask about the Hubble tension, because you've talked a lot about the anomaly faced by lambda CDM with regard to the BAO data. But how do some of the models you discussed today, like pair, when you bear in mind the locally measured Hubble constant? And I know some of the people in the audience were involved in measuring in that.
So I'm not interested in the Hubble tension, sorry. It's one of those things where, I'm following George Evstathiou's maxim that he used at the Royal Society meeting last year, which is, I'm going to park that for now. And
Okay.
it's a matter of choice.
Okay, thanks.
Thank you. And Philip?
Yes, so is the signal for evolving dark energy coming only from the DAISY results? And if so, what are the prospects for getting some sort of independent evidence for that from another survey, completely different method, whatever?
So the evidence for evolving dark energy, there's evidence from the supernova results, there's evidence from the DAISY results. Arguably, and I just want to make a very clear statement, which is, at the moment, I'm still completely agnostic about the data. I'm still not sure, whether there might be things hidden there. I'm partial to some of the things my colleagues have said about whether the data is strong enough or not. But I'm just exploring, if we take the data, where that goes. DESI on its own has a reasonable evidence for it. Supernova on its own has reasonable evidence for it. You combine them and the evidence is stronger. There will be new data coming along. Euclid will bring new data. There are low Z samples for the supernova, like ZTF and Atlas, which will be crucial for the low Z point in the supernova data plot, which plays a huge role. The low Z point is very, very important. So I think there will be progress.
So I think we can thank Pedro again. Thank you so much.